All right, let's dive right into this explainer. Today, we're unraveling a massive, hidden timing bug inside an AI-generated hardware core. We're talking about a physical computer chip designed completely by artificial intelligence. And honestly, this isn't just a standard bug fix. It is a full-blown engineering whodunit that takes us right to the bleeding edge between software simulation and physical hard silicon reality. If you're a fan of solving complex mysteries through pure structured reasoning, you are absolutely going to love this. Picture this. You boot up your newly minted hardware and boom, it works perfectly on the very first try. An LED starts blinking exactly the way it was programmed to. Sounds like a total win, right? Well, not quite. As we're about to see, that little blinking LED was actually a perfect illusion, hiding a completely fatal flaw deep inside the logic. It's a fantastic reminder that just because a system looks like it's humming along nicely on the outside, it doesn't mean it's actually functioning correctly under the hood.
Part 1. The Perfect Illusion.
So, let's set the scene of the crime. June 10, 2026. This brand new AI-generated core powers on for the very first time. The setup was wonderfully compact, running on a physical DE10 nanoboard with a Cyclone 5 chip ticking away at 50 megahertz. We are talking super minimal logic here, barely 235 logic elements and a couple of memory blocks. They also use a prescaler set to 50,000, which is basically just a giant wait timer that slows the chip's actions down enough so human eyes can actually perceive the LED blinking. And the result? Instant blinking, first try. But beneath that flawless exterior, a massive error. The chip was executing literally every single instruction exactly one clock cycle late. So why on earth didn't that blinking LED give the error away? Well, it comes down to a phenomenon we call constant shift execution. You see, a simple blinky program is incredibly forgiving because every single instruction is delayed by exactly the same amount of time, one state late, but completely in the right sequential order. The logic of the program still holds together. The jump command still wraps around. And when you factor in that massive prescaler waiting 50,000 clocks between every visible action, that tiny one clock slip is just buried completely. Now, what's genuinely wild about this is that Claude Code actually predicted it. Before the physical hardware even ran, the AI audited its own code and flagged a mismatch. It pointed out that the finite state machine, the central brain directing all the traffic, was executing a stale instruction. It practically warned the human architect right then and there, hey, just because this code blinks an LED doesn't mean it's actually mathematically correct.
Part 2. AI's Vendor IP Blind Spot.
To understand exactly how this bug snuck in, we need to look at a major blind spot in how AIs handle standard hardware components. The core issue is this. AI flat out refuses to use vendor-specific IP, like Altera's M10K memory blocks, which are physical specialized blocks of memory on the chip. Why? Because the AI simply doesn't have the proprietary simulation models to verify them, so it retreats to safe territory. It only builds what it can prove mathematically. But on a physical FPGA, you absolutely need those specific vendor components if you want your chip to run efficiently. To solve this, the human architect pulled off a pretty brilliant workaround. They built a wrapper module that completely bypassed the AI's hesitation. Inside this wrapper, they created two separate branches. First, a portable behavioral branch that the AI could fully simulate, verify, and be happy with. Second, a specific vendor branch that the human would use to actually build the physical hardware. Finally, they made the whole thing switchable using an explicit parameter. It was kind of a Jekyll and Hyde setup, allowing the AI to work without hitting a brick wall. But here is the catch. The golden rule for this trick to work is that the behavioral branch, the one the AI sees, must perfectly reproduce the actual silicon's read latency. The wrapper had a strict registered contract saying, hey, reading memory takes one clock cycle, because physical M10K memory takes exactly one cycle to read. However, the AI had initially built its finite state machine expecting magical, zero latency combinational memory. That subtle disconnect between the AI's zero latency expectation and the real-world one-cycle reality, that right there is our root cause.
Part 3. The Smoking Gun. Address 05H.
That latency mismatch leads us straight to the physical proof of the crime. The architect hooked up a signal tap logic analyzer directly to the silicon's address bus to literally catch the chip in the act. And bam, there was the smoking gun. Address 05H showed up right there on the bus. Now, you might be thinking, what's the big deal with 05H? Well, the Blinky program is tiny. It only takes up memory states 0 through 4. At state 4, the code explicitly tells the machine to jump back to state 1, meaning physically and logically, address 05H literally should not exist. There is zero code path that goes there. Seeing 05H pop up proved that the AI's early desk prediction was 100% accurate. Because the memory took a full clock cycle to return the data, the machine stumbled in the dark for a split second. We call this the stale clock fetch. The chip decoded the jump command one cycle too late. In that tiny window, the state counter kept ticking, pushed past the end of the program, and blindly grabbed address 05H from uninitialized memory before the jump command finally snapped it back to reality. Part 4. The Half-Clock Cure. So how do we fix it? The architect proposed a resolution so elegant it's honestly beautiful. Instead of ripping up and rewriting the entire finite state machine, they suggested simply clocking the physical memory on the falling edge of the clock signal, the exact moment the electrical pulse dips, instead of the rising edge. Think about it. At 0 nanoseconds on the rising edge, the brain asks for an address. At 10 nanoseconds on the falling edge, the memory captures it. By the time the very next rising edge hits at 20 nanoseconds, the data is already waiting. The geometry of the electrical signals literally heals itself within a single clock cycle. This half-clock cure was an absolute game changer. For starters, it perfectly simulated zero latency for the AI, meaning zero changes were needed for the finite state machine. It kept the incredibly clean, one clock per opcode design intact. And sure, reading on a falling edge cuts your timing budget in half, leaving you with about 10 nanoseconds. But at 50 megahertz, that is plenty of time. So fixing this highly complex bug was essentially completely free. Actually, getting this fix verified in simulation, though, not quite as simple. This quote really hits the nail on the head regarding hardware engineering. The test bench, the simulation program acting as the judge to verify the fix, actually tripped up twice trying to capture this exact half-clock sampling moment. It perfectly proves that human-written comments can totally deceive you. The only absolute truth in a timing contract comes down to explicitly checked parameters and assertions. Once that half-clock cure was dialed in and verified, the hardware was synthesized again. They ran a brand new logic analyzer capture, and the sequence was perfectly healed. The jump command landed exactly on the correct clock, 01, 02, 03, 04, and safely back to 01. Address 05H was banished forever. No way it was coming back. Part 5. The 4 Tiers. With the bug squashed, let's zoom out a bit and look at the whole methodology that made this possible. The project moved through 4 distinct tiers to validate the spec. For comprehension and deliberation, asking, can it be understood and can it be reasoned over, they utilized Gemini 3.5 Flash. For implementation, meaning actually building the code, they used Claude Code. But for that critical 4th tier, silicon, asking, is this actually true on physical hardware, they needed a physical witness, and that was the SignalTap instrument. And here is the absolute biggest takeaway from this entire explainer. This bug lived squarely in the shadowy seam between an AI's software simulation and the physical reality of silicon. It was caught for one reason and one reason only. A human architect knew exactly where to point a physical instrument, based entirely on where the AI pointed a theoretical prediction. Neither the AI nor the human could have solved this alone. Because of this incredible synergy, the development loop for this core is now unbelievably fast. You can load new code directly over a JTAG connection, physical cables straight to the chip, with zero time-consuming resynthesis required. Plus, thanks to that wrapper workaround we talked about, the library of standard vendor IP that the AI can actually verify is expanding, paving the way for some seriously complex AI-assisted chips in the future. I love this thought from the source material. An address that should not exist is worth 1,000 passing tests. Finding that impossible 05H address validated everything. It proved the immense, critical value of aligning your simulation models with cold, hard, physical reality, rather than just cheering because an LED happened to blink on the outside. So the loop between the AI's desk and the physical chip is officially closed. The spec is understood, built, and true on silicon. But it leaves us with a pretty fascinating question. As we push these AI-generated cores to handle higher frequencies and far more complex tasks, what other bizarre physical mysteries are waiting for us? Are we truly ready for the 5th tier, pure engineering? Thanks so much for diving into the silicon with us today.